Hey everyone, thank you very much for coming. My name's Josh Gordon. I work in TensorFlow Developer Relations. And I'm really excited to share with you some thoughts on deep learning today, a whole bunch of resources you can use to learn much more about it, and a pair of my favorite open source models for image classification, natural language parsing, and some neat tricks you can do with these. And I'll also show you some cool things and how you can actually use a pre-trained image classification network to generate your own artwork, which I find really interesting. So before we get started, I just wanted to take a moment to reflect on this idea of reproducible research. So we can do a lot of things today with deep learning that I think we take for granted. So in 2005, I spent about 6 months trying to do basic image classification. I was working in a medical lab, and we had a slide containing some solution with some cells on it. And my goal was to use a neural network to identify cells that were diseased and cells that were healthy. So I was literally just tagging regions of an image. And there were many machine learning libraries in 2005, including some great ones that I still use today in a teaching setting, like Weka, which I absolutely love. But we were still writing a lot of our neural network code by hand. And it took us about 6 months to get a network that worked well just for this binary classification task. And it was really hard to experiment with different network architectures and different optimizers. And what's interesting, we had a lot of really good engineers working with us. And doing this type of image classification today looks very different. So today, a strong Python developer with some basic background in TensorFlow and willingness to try different open source models and read some literature could do a much, much, much better job than I could have done in 6 months, like full time, in just a few days. And so there's really been a lot of value created. And the reason that we can do all these great things is that a lot of researchers, academics, and developers, both from universities and Google and other large companies and small, have been, I think, very generous in sharing their tools and their ideas and their code so that the next generation of developers can iterate and refine on their ideas. So we have a lot of value at our fingertips. And because I started my machine learning career in medicine, I just also wanted to take a moment to reflect on some value that's been created by a lot of this reproducible research and these open source models. And so here are 3 applications of medical imaging from the last 8 months or so. And they all rely on an open source TensorFlow model that I'll show you today called Inception. And Inception is one of the world's most accurate image classifiers. It's completely open source, which means you can check it out and train it on your own data to classify things you care about. Here we're looking at work in diabetic retinopathy. I'm going clockwise from the top left. Diabetic retinopathy, and the basic idea here is there's an eye disease, and if it's caught early, it's treatable. And if it's caught late, it can lead to blindness. And so in this work, we're using image recognition to identify patients in need of care. The next image here was a Nature paper from Stanford University. And this was using TensorFlow and image classification actually on Android to detect skin cancer. And the cool thing about this is that I don't mind going to the doctor, but I'm kind of a lazy guy. But if I had an Android app that I could just quickly scan my arm to find out if something was malignant or not, I'm much more likely to do advanced screening. And then in the lower left, we have work using image classification in medical pathology. And the idea here is you have a pathologist, and their job is to take a look at a slide and find cells that are cancerous. The problem is these slides can be enormous. They can be 100,000 pixels by 100,000 pixels. So we're talking about billions of pixels on this slide. And they might be looking for a small region that contains cancerous cells. And so you can imagine that scanning these slides by hand can be incredibly demanding. But of course, if you have an image recognition model, you can analyze every single region on that image with a fine-tooth comb. And you can really build tools to assist physicians in their diagnostic work. So we can also do awesome, fun things with like art and music and sound, but there's also, like, I think, real humanitarian value here that's becoming increasingly accessible. And the reason I really like this medical stuff is this is a field that is not computer science. But because of a lot of reproducible work in deep learning, we're seeing a lot of value being created in many disciplines, including things you wouldn't expect, like artwork. So I mentioned the word deep learning a couple of times. And so here I'd like to show you a cartoon diagram of a fully connected deep neural network. And this particular network is classifying this image as a cat or a dog. And I wanted to show you this to highlight one of the differences with deep learning and some of the work I was doing in, say, 2005. So the way I would have written an image classifier in 2005 is I would have written a lot of Python code to extract features from the image. I would have thought about what features do I want to feed into my classifier. And this would be lines and shapes, colors. I might have used a library like OpenCV to do face detection. But in deep learning, we can give the classifier the raw pixels from the image. And we'll let the network find good features on its own. And we can actually visualize what it learns later. The reason this is called a deep neural network is there is more than one layer. We have a stack of layers. It's a deep neural network. That's where the term deep learning comes from. And at the very top, this network happens to be classifying that image as a cat or a dog. There are many wonderful deep learning libraries, but of course my favorite is TensorFlow. It's from Google, and as you guys probably know, it's used both for research and production. This means that TensorFlow has everything you need to build products with hundreds of millions of users, like Google Photos, as well as do actual research, like the work you saw in medical imaging. And having the same code base for both of these is very valuable. So these are the, I'm going to have to fly through this, by the way. I have a lot of content that I want to share with you, so I'm going to have to accelerate a little bit. So here are some of the papers. Well, these are actually blog posts, but all of them point to a paper that I'd like to share with you today and show you how you can do practical and fun things with them. And of course, there's much, much, much more. Google research in the last couple years has been prolific in publishing papers. And many of these are state-of-the-art. And often, in addition to the paper, they publish everything you need to try this out on your own. And I'm going to show you what that means. So one question that comes up, if you have a, say, state-of-the-art natural language parser, that has a lot of business value. And one question that's asked to me a lot is, well, why open source that? Why share it? And one really important reason is that it empowers others to continue your ideas. So I'm not doing research now, but even as just a hacker, I have many more projects than I will ever finish in my lifetime. Because you guys are all busy, there's not enough hours in the day. But by open sourcing your code, you make it possible for the next generation to continue your line of thought. And then another huge benefit is that it reduces barriers to entry. So rather than having to design your own image classifier from scratch, you can immediately go to this state-of-the-art in open source and get started right away on the problems that you care about. So briefly, here's what makes a good, reproducible open source release. Of course, you want to share your code, but in machine learning, you want to share all of the code. That means the code you need for inference, for training, as well as for evaluation. So you can't have any hidden pieces. Otherwise, it's not reproducible. You always want to share the data set that you used to train the model. I know sometimes there's lots of copyright issues, especially if you're working with images, but you should at least make it reproducible. It's also really helpful to include a toy data set when you share a model. And by a toy data set, I mean a small piece that makes it really easy for someone to test if their end-to-end pipeline is working properly. A pre-trained checkpoint is super valuable. So I believe the first implementation of Inception, and this was about a year ago, took something like a week to train on a machine with 8 GPUs. Of course, not everyone happens to have 8 GPUs sitting around. So by sharing a pre-trained checkpoint, that means the model works out of the box to classify images, and it makes it much faster to explore with. And then something that I'm a recent convert to is Docker. So oftentimes, you have a lot of dependencies in your environment. And so by sharing a Docker container, it makes it much faster for people to try your ideas. So this talk is about open source models, but of course, you can also develop with deep learning by writing code. And briefly, I want to show you what that looks like. So the point I want to make is that developing with deep learning does not have to be hard. With basic Python skills, you can write neural networks in something like 15 lines of code now. So this is code from a library called Keras, which is a high-level machine learning API that I really like. It's very concise, and it's fully supported in TensorFlow. And the idea is that in TensorFlow, you'll get the best of both worlds. And here is almost the entire code to define a network very similar to that cartoon diagram we saw earlier. I'm adding a stack of layers, and most of the work here is going into making sure that the weights and the sizes all line up. I got to pick up the pace of this. Here's code to compile the model. And so in deep learning, if you're learning it for the first time, one thing to be aware of is you'll run into a whole lot of new terminology. And oftentimes, the terminology you encounter can be quite scary. Like here, we're looking at something that says loss equals categorical cross-entropy. And the first time I saw that, I was like, oh my God, this is incredibly different from a lot of stuff I've worked with in the past. But oftentimes, when you look at these terms, they're simpler than they sound. So loss in deep learning just means error, and it's just a number. And categorical cross-entropy is just a fancy word for comparing two distributions. So there's a distribution that you predict, and there's a distribution you should have predicted. And that will just give you a number that says how different they were. I also want to let you know that TensorFlow comes with a nice visualization tool called TensorBoard. And as you can see from this animation that has failed spectacularly, you can use TensorBoard to actually visualize the neural network that you defined and actually poke inside the layers. So the second way to get started with deep learning is to leverage open source, which is what I want to focus on today. And the first model I want to talk about is Inception. And I'll show you how you can use Inception for image classification, as well as deep dream and style transfer. So before we saw a cartoon neural network, but here's what Inception actually looks like. You can see it's much larger, it has many more layers, and inside the layers there's more moving parts. And when you're defining a network like Inception, this is somewhere where TensorFlow really begins to shine. And tools like TensorBoard make it really easy to spot any errors that you have in your architecture. So first I want to talk about image classification. So I'm from New York, so here's a picture I snapped last week looking north towards Central Park from the office. And when you're doing image classification, the easiest way to get started is to use an API. And I just want to show you what this looks like. So this is the Google Cloud Vision API. It's drag and drop, and there's also a RESTful interface. And basically, you can classify the image, and you'll get a set of tags back. So here, this is a skyline, city, metropolis, whatever. But you can also do this in open source. And you can do this actually quite easily. So here's code for Keras running inside TensorFlow. And this is actually the complete code on this slide. It's complete. And this code will actually import Inception, which is a network architecture that we saw on the previous slide. It will load the pre-trained weights from a checkpoint and pre-process and classify an image. And so this stuff is much, much more accessible than it often seems. And this right here in these, like, whatever, 5 lines of code is much, much, much better than what I could have done just a few years ago with a huge amount of effort. And the funny thing about Inception out of the box is if you classify this image, you get nonsensical tags back. So here, Inception is telling me that this is a valley and possibly a doormat. And the reason why that is, and it's not a problem, the reason why that is the pre-trained model that comes with Inception is from a data set called ImageNet. And ImageNet has 1 million different images from 1,000 different categories. But most of them are pictures of dogs, cats, flowers, artwork. And so, of course, image classifiers only can recognize the things they've been trained on. So Inception doesn't know any better when you get started. And in fact, the blog post that announced the latest version of Inception is very proud that out of the box, Inception is actually sensitive enough to tell the difference between these 2 different species of dogs. One's a Malamute and one's a Husky. And it's this sensitivity that, when you retrain Inception on different data, makes it very good in the medical diagnosis domain. And in fact, there's a good expression, don't trust but verify. If you run Inception on this image, you'll actually get output that's more sensible. So it will identify it correctly as a dog. So probably you don't care about recognizing dogs. So how can you take Inception and retrain it to recognize images that you care about? And the good news is there's this concept in machine learning called transfer learning that I want to briefly introduce and then show you how accessible it is. So the idea in transfer learning is simple. And that's, if you have learned a neural network to, say, recognize dogs, and now you want to recognize, say, cities, do you really need to start from scratch? While you're learning to recognize dogs, the network has probably identified useful features and images that might be applicable to other things. So instead of throwing away the network that you've previously learned and retraining from scratch, instead you can do surgery on the network. You can chop off the very last layer of weights and create output nodes just for the classes you care about. And then instead of relearning the entire network, which might take a week and 1 million images, you can relearn just the very last layer. And you can do that in 30 seconds, and you might only need 100 images. So with a very small amount of data, you can actually create your own image classifier. And I wanted to let you know we have a code lab for this, and just a couple days ago, we published a second version of it called TensorFlow for Poets. And TensorFlow for Poets is dead simple. It's basically going to run a bunch of scripts for you that do that surgery on the network. And the only thing you need to train a very high accuracy custom classifier is literally to collect directories of images that you care about. So what we're looking at here is an app that I built at the Metropolitan Museum of Art in New York. And I can point at paintings and sculptures, and it will tell me which one it is. And Poets 1 and 2 will actually walk you through training a classifier and installing it onto an Android. A hilarious piece of criticism that I got about TensorFlow for Poets was some developers felt that it was too easy. And TensorFlow for Poets is a really easy code lab. It's not meant to go into the details of how transfer learning works, but we have TensorFlow tutorials for that if you're interested. But there's something really important about TensorFlow for Poets. A lot of using machine learning in practice is not about thinking really carefully about how to define models and like using sophisticated algorithms and lots of math. A lot of machine learning is just like development in general. If you're building an app, like this one at the museum, you have to think carefully about how is this app going to be used in production. So if a user picks it up and they point it at a painting or a sculpture, you have to think about things like, what if it's dark? What if there's someone in the background? What if there's an obstruction? And so a lot of thinking in machine learning is how can you collect training data to cover these different cases? And if you do that properly, then you'll have an app that works very well in practice. And for Android developers here, I wanted to let you know we have 3 Android samples for TensorFlow. The one on the far left is doing something called style transfer, which I'll show in a sec. It's beautiful. The one in the middle is an image classifier, which runs Inception. And the one on the right is an object detector, which can help you identify the location of things in images. So one really, really fascinating thing about deep learning that I would just want to give you a preview of is that when you learn an image classifier, in addition to being able to classify images, that classifier actually has gained some knowledge about images in general. And you can use that knowledge, surprisingly, to generate art. I'm running behind, so I'm going to skip that, and we're going to go straight into Deep Dream. So, question. How many people have heard of or tried Deep Dream? So, like half, right. How many people know why it's important? Much fewer. So, to me, the point of Deep Dream is not that we can generate beautiful psychedelic artwork. Like, that's really wonderful, but that's not why Deep Dream is fascinating to me. The reason that I find Deep Dream interesting is it really begins to investigate the question, why is it that deep neural networks are so good at recognizing images? And there's things we know about deep learning in general, why they're so effective. Of course, with like GPUs and cloud, we can train larger networks on much more data. So that's one reason why networks are so good. Another reason is there's been many algorithmic improvements over the last few years that enable you to train networks more efficiently. These are things like different initialization strategies, or optimizers, or batch norm. But the reason, in my view, that why deep neural networks are so good at recognizing images is they automatically learn features. So I mentioned with that cartoon diagram at the start that the network will find useful features from images automatically. And in addition to finding useful features, networks actually learn a hierarchy of those features. So in most image recognition networks, you're using something called convolution. And I wanted to give you a preview of what convolution looks like. So when I say convolution, what I really mean is using a filter. And so on the left, we have a grayscale picture of Manhattan. In the center, we have a 3x3 filter. And on the right, we have another image that shows very roughly the edges of where the buildings are. This kernel or filter is a little edge detector that I wrote. It's very scrappy, but if you write Python code to slide this filter along the image and compute the dot product of what's beneath it at each location, it will produce that image, which roughly shows the edges. So this filter is hand-engineered, but in convolutional neural networks, we're going to learn a hierarchy of these things. So here, I've added a line of Keras that's going to learn 32 of these filters. And each of these filters is going to be learned as a function of the raw input image, so as a function of the pixels. But if you have a stack of these filters, what you're doing is you have the first layer is finding features of the raw image. The second layer of filters is learning features of features. And the third layer is learning features of features of features. So the filters that you learn become increasingly abstract, and you get this for free by virtue of training an image classifier. You get this learned hierarchy of filters. And what I've done here is, and you can repeat this with the code of the GU link, is I've started from random noise, and I've optimized the noise to increasingly excite filters at different layers of the network. And the really interesting thing, and I think there's really good science to be done here in really understanding this rigorously, is that the lowest layer of filters generally learns to detect edges and colors. The next layer is learning textures. Those are features of edges and colors. And then as you move higher up the network, you begin to learn things like patterns. And if you go way high up the network, which I'll show you later, that's when you get psychedelic stuff. And so Deep Dream doesn't have to be used to create trippy artwork. As you'll see in a moment, I'm not an artist, but what I tried to do is use Deep Dream to turn this image into something like a firework display. And to do this, you can actually select which filter you want to optimize for. If you look at the Deep Dream notebook at the GU link on the top, you're going to see a whole lot of code. But the interesting thing is that something like 90% of that code is fine-tuning, just to make sure that the images that are produced are really beautiful. This is basically the core of the Deep Dream algorithm, and it's really, really concise. So the basic idea in TensorFlow here is that we're going to pick some filter from some layer of the network, and we're going to define a loss function. The loss is just a number, and here the loss is going to tell us, on average, how excited is this filter by some image. So if we classify any random image, the filter is going to get some activation. And in Deep Dream, what we can do is we can say, TensorFlow, please tell me the gradient of this loss with respect to my image. And you're asking TensorFlow, given an image, how should I modify that to increasingly excite some filter in the network? And then what you can do is you can literally modify the image according to the gradient. And here I can actually add it directly to the image and repeat. And so your image will progressively excite a filter. And that's where Deep Dream comes from. So here's another picture I took from the reservoir in New York. And we're looking south from 90th Street. And I ran Deep Dream on top of it using a filter at a very high level of the network. And this particular filter, actually, I'm sorry, I ran it on a whole layer of the network, the second to last layer. And if you run Deep Dream on an entire layer, what you're really saying is, TensorFlow, please progressively modify the image to excite all the filters. So you're basically super saturating it with things that it knows how to recognize. And that's why you see, if you use Inception, that's why you see dogs and cats and snakes and stuff like that everywhere. But if you took Inception and you retrained it, say on artwork, and then you ran Deep Dream on top of that, you would no longer have these dogs. Instead, you might modify an image to contain elements of like Monet and Picasso. So it's cool, but I think there's good science there. I didn't want to show you this here, but the notebook actually contains code to produce your own animated dreams. But it was borderline not safe for work, not in like a strange sense. It was just almost, it was too psychedelic and seizure-inducing. So there's another absolutely beautiful thing you can do with pre-trained image networks. And this is called style transfer. And for people new to it, I can't recommend this strongly enough. It is my favorite way to produce really beautiful artwork. So what I want to show you is something from a project called Magenta. There's going to be a talk on Magenta tomorrow by Douglas Eck, who's one of the project leads. Magenta is a wonderful project, and it investigates how you can use deep learning to generate art and music. And they've done a great job. So here, in style transfer, the idea is that you begin with a painting. And here's one from the Museum of Modern Art in New York. And then you take a photograph. So here's one of the Golden Gate Bridge. And the goal in style transfer is to produce a new piece of artwork that combines the style of the painting with the content of the photograph. And by style, I mean things like edges and shapes and colors. And by content, I mean things that are semantic, like here I see a bridge. And so if you try to do this by hand, or in Photoshop or whatever, to produce a new painting, the result would probably not be very good, unless you're much better at Photoshop than I am. But using style transfer, you can actually generate images like this, which are astoundingly good. And the reason I find this so interesting is you're able to produce images like this almost for free as an artifact of training an image classifier. And in Deep Dream, what we were doing is finding an image that maximally excites some filter of the network. But in style transfer, we need to somehow caption the notion of content and style. And here's a high-level diagram of how that works. We also get this for free. If you take, say, the painting on the top, and you use some existing image classifier, and you just classify the painting, what you can do is look at the activations of the lower half of the layers, roughly. Earlier, we saw that the first layer detected edges, shapes, and colors and textures, say in the first three. And so when you classify the image, by looking at the activations in those layers, in some sense, you can capture what it means to have style. And then if you classify the photograph, and you look at the activations towards the top of the network, you have some sense of what it means to have content. And then if you combine those, you can actually come up with a number that you can optimize in TensorFlow. And that's how you actually can start with random noise and progressively optimize it to minimize a loss that combines content and style. And so at a high level, that's how it works. But I think the science behind it is mind-blowing. So this is a good example in deep learning of something that never in 100 years would I have thought that ever I could write a Python program to produce images like that stylized bridge. It just never would have happened. But it turns out that this is something we get for free. And you'll see in Douglas's talk, if you go, which I highly recommend, you can actually do style transfer in real time now. And here, what they're doing is they have a collection of paintings, and they're saying, I'd like to apply some more Starry Night to this dog. All right. So that's inception. Language is also obviously really important. People that work in like robotics or like video or images or games have the best demos. So their work is usually more well known. But obviously, almost all the apps we write work with text. So here I want to show you a couple models from the SyntaxNet family. Well, actually, just one, Parsysaurus. And Parsysaurus is currently the world's most accurate natural language processor. And it's completely open source in TensorFlow. So here's how we can work with text. So imagine you just have a simple sentence, I love NYC. One thing you can do if you go the API route is you can use something like the Cloud Natural Language API to analyze this sentence. It's drag and drop. There's a web demo, which is actually really fun. And it's also RESTful if you write code. So here, we're seeing the Cloud API telling us that love is a verb, and it's looking at a dependency parse, so we can find out that NYC is the direct object of the sentence. But you can also do this in open source TensorFlow. And so here is a single line of code to start up a Docker container for SyntaxNet. And this will contain the Parsysaurus model, as well as code for over 40 different languages. And using this, you can actually do some really interesting things. So parsing McParseface from last year, McParseface was previously the world's most accurate natural language parser. And McParseface has been superseded by Parsysaurus. The main difference, well, one of the differences between them is that parsing McParseface operated on words. So the tokens that it would analyze would be the, go stack, distims. But Parsysaurus operates on characters, so it's much finer grained. This is a quote from a book called The Meaning of Meaning. And if you look at it, this sentence is nonsensical. But what's really funny is for some reason our brain actually knows a whole lot about this sentence. So for instance, I could ask you some questions about it. So what do you think the part of speech is for distims? Is distims a noun? Is distims a verb? It's a verb. And it's funny that we know that, because it's not a word. And the really interesting thing is you can actually use Parsysaurus to tell you that as well. So if you fire up that Docker container, you'll find an IPython notebook called the Interactive Text Analyzer. And with just a few lines of code, you can feed Parsysaurus that sentence. You can get back a bunch of tokens, which are protobufs that contain a whole bunch of information about the parse. You can iterate over it, find the distims word, and print out the part of speech tag. And Parsysaurus will tell you that that's distims. You can also ask the question, who or what is doing the distimming? And is it the dashes that are distimming, or is it the go stack? And when I read this, I see it. It's the go stack is the thing that's doing the distimming. And Parsysaurus can tell you that as well. So if you iterate over the tokens, we can find the subject of the sentence. And you'll find out that's the go stack. Parsysaurus can also tell you a lot more about a sentence like this. So if you just print out the raw protobufs from all the tokens, you'll get a whole slew of information, and only some of it is actually on this slide. So it actually can give you pretty fine-grained stuff. Like, for instance, it can tell you that distims is in the present tense. It can tell you that the go stack is singular, and it can tell you that the dashes are plural. And then the Natural Language API has these beautiful dependency trees, but you can actually produce that as well. And so the notebook actually contains code using good old GraphViz to produce something that looks exactly like this. And there you can see that the dashes is the object of the sentence. So there's a lot of value in open source. And the cool thing about Parsysaurus is that multilingual support is obviously really important. And I'm really, really impressed by the SyntaxNet team, as well as the Magenta team and the Inception team, because out of the box, they actually have a link where you can download pre-trained models for 40 different languages, or more than 40, actually. Loading these languages, it's a little bit, there's a few more parameters, but it's really 1 or 2 lines of code. And so you can switch the model to German, just like that, and here are the languages that I saw out of the box. So this is actually really cool, because if you're building any kind of application that works with text and is doing something machine learning-y, you can think about multilingual support from the start. There's two really good use cases for this. The first is an easy way to get started, and if you have an existing system which is doing some sort of text classification, this could be sentiment analysis, you could be doing spam detection, whatever, and you're using part-of-speech tags or dependency tags, you can use a model like Parsesource to get a slight boost in your accuracy. But I think more importantly, you can use this as a foundation for a new system. So anytime you're training a model in deep learning, you're going to need lots of data. And I think by using these features as additional input, you can reduce the amount of data that you need because you're not going to have to learn notions like part-of-speech and dependency tags from scratch. Instead, you get them for free. There's a really awesome term that I found on Magenta's blog, and it's called release++. And so this is some text that I actually stole from their article where they're talking about something called nsynth, which is actually a program that can generate sounds. And I thought this was a really beautiful passage. So when they shared the code for nsynth, they explicitly called out, sure, they're sharing the code, but they're also sharing pre-trained models and a Docker container. And because the team has done such a wonderful job of doing this, it means that if you want to try out their work, especially in style transfer, you can do it out of the box, and it works very, very well. And it sounds simple, but that's actually something really hard to achieve in practice. Like, I can't tell you how much time I spend playing with open source software and machine learning, whether it's written in TensorFlow or a different toolkit, and it is so hard to actually replicate results. And so I think some of the work that I've showed you today is good examples of work that sets the bar on really how to share ideas. I think I've accelerated too much in my speed, in my rush to get through all this content. But anyway, a blessing and a curse of learning deep learning today is that there are a huge number of educational resources. There's actually an entire Medium blog post where somebody actually very helpfully went through something like 30 different machine learning courses and looked at all the reviews. So here are just a couple that I'd recommend. Stanford has a great course. It's actually student-initiated. It's really impressive on TensorFlow, CS20SI. It has an intimidating title. The title is like TensorFlow for Deep Learning Research. But really, a lot of this course will actually walk you through the basics of writing TensorFlow programs. If you're new to neural networks, the course notes from CS231N are outstanding. That course also has a slightly intimidating title. It's Introduction to Convolutional Neural Networks. But the beginning of the class will actually walk you through, just in Python, it doesn't use TensorFlow at all, really what is a classifier, how do you write one from scratch, and then it will take you from something like k-nearest neighbors all the way up to a convolutional neural network. If you like natural language processing, although it's not on the slide, Stanford also has, I believe, CS224N, which is actually a course in doing natural language processing with TensorFlow. And then there's a wonderful blog if you'd like to get some intuition for how neural networks actually work under the hood and why they're so good at recognizing images and doing other things. Chris Ola's blog is absolutely outstanding, and I highly recommend it. So thanks very much. One of my favorite things about I/O is just actually looking at the crowd. I see a bunch of folks that I haven't seen for about a year. So I like this conference a lot. I'll be around if you have any questions, and I'm happy to chat afterwards. So thank you very much, guys, and I hope these resources are useful.